In this lab 5 section, we'll discuss about the memory modeling. This is important in the perspective of your project 2. Project 2, we have already modeled the memory for you. So you don't need to worry about that, but you need to study it a little bit carefully to model the register file, which you need to do. So memory modeling, register modeling, file modeling are pretty much similar with a little bit difference from each other. So this is one of the important thing you need to be very attentive about on the memory modeling side. So here what we are trying to do is to model a 256 megabyte memory with 32-bit word line. This means I have like 64 meg address to access the data from the memory, and since it's 64 meg address line, we need to have 26 bit of the address bus, and we have the data as 32-bit word, and we have only one single port for data, either in or out. So when we are reading the memory, data is out from the memory through this port on this line, but when we are reading, data will be in from whoever is driving or trying to write into the memory. For our case, it's a processor. We'll go and write the data, push the data through this port, same in-out port, into the memory for writing. And we have control signal like reset, which is the reset on the negative edge, which means like when reset has to be on the high for the normal operation of the memory, and if it goes low, then it will clear up the content of the memory, and it becomes basically all zero value inside the memory. It's synchronous with the positive edge of the clock, so all the read-write operation will be done at the positive edge of the clock. There are control lines like read and write. If read is 1 and write is 0, it's the read mode, so data will be coming out through the data port. If it is read 0, write 1, it is a write, so whatever data is set into this line, it will be written in at this specified address. And if they are both 0 or both 1, read and write both 0, both 1, then this data will be placed at a high Z, electrical isolation state. Okay, so now let's see how we model it in the Verilog. So we start with a module, give a module name like the memory 64 MB, then we list down all the ports. We know what are the ports. Actually all of them are input port except for the data which is in output. Okay, so then we'll coming back to the parameter file a little bit later, but let's put the obvious thing out of the way. The input we list down as a 1-bit input, read, write, clock, reset, and we have of course the address bit of 26-bit bus, and this is the macro which is address index limit, which is being used as which is being defined into the prj underscore definition.b file. And the output the output is is data, which is data index limit, which is 32-bit. It is again defined the data index limit, that macro defined in that prj underscore definition.b file. So these are the list of port, and the parameter file. This parameter file is basically is an variable which is defined under the module. Under any module we can define a parameter, and in that case it becomes a parameterized module with the initial value. It can be anything. We make it as a string with a file name, mem content of one.dat, that is the default value. But when we instantiate this memory, like in some upper block in the hierarchy, we can always redefine this value of this parameter. We can just say memory content 2 dot dat. Okay, so that whenever this is instantiated, the instantiation parameter value will be in that case memory content 2 dot dat. So we can control the kind of behavior of a module through this parameter. In some way, like some of the module, like let's say for example ALU, usually it is 32-bit the data bit, but we can parameterize to make it like 64-bit or 128-bit ALU and stuff like that. We just define a parameter of my data width is 32 by default, and then when you instantiate the ALU, we just put that parameter as 64. So instantly that ALU would become a 64-bit. But anyway, so that is the we use this memory init file. We'll describe it later in a minute, but essentially it is basically contains some of the data which will be loaded in the memory in our memory model at the reset time. Okay, now how do we actually define the storage? We define the storage, we name the storage as SRAM 32 cross 64M, which is essentially a two-dimensional array with data index 32-bit value each address line, an array of 32-bit which is spanning from 0 to 2 to the power 26 minus 1. This is the value again in the purge underscore definition.v. Okay, so this two-dimensional array defines our memory storage for our memory. Integer I will see we index use that as an index in the reset operation, and then we use some register 32-bit register called data 32-bit storage. So by the way, this register is not as the register we are starting as an hardware register. No, these are all the internal storage of a simulator. Okay, so now we do, this is very important line, the data in out, that port, you know, that this port is in out. How do we control values on that data? Essentially what we need to do is during the read operation, the memory module should drive that data line. Okay, but in any other case it should put the line in a electrical isolation state. Why? Because let's say it is a write operation, and during the write operation, if this guy is driving some data out on that line, and this memory is connected to, let's say, another module, right? This port, data port, is connected to the data port of the processor. The processor is trying to write on the data line, and it is also driving some value on the data. So that becomes pretty much a rest condition, right? The memory is putting the data in the write cycle, and processor also putting the data on the same line on the write cycle. So it becomes a rest or contention, memory contention, okay, data line contention. So what we need to do, if we need to detect if it is a read operation, then only drive the data from inside the memory. So we do that through this statement, read 1, write 0, which is a read statement, then assign data as an data return register value, which is basically read operation. You are pushing out the data through the data port. Everything else make it a 32-bit high Z. So see, we use the replicator operator here, which tells me, okay, replicate this 1-bit Z value, high Z value, 32 times. Data width is 32, defined in the purge underscore definition.v file. So this is essentially does it. So the other module, which is basically connected to this proc, we'll see it in more details when we review the file project to files on the processor code. We'll see that it is driving, it is connecting an in-out port from it through the data. It exactly the reverse. What that processor, which is external to the memory, which has similar assignment statement, but it is at the write operation that guy is driving, everything else become high Z for it. Okay, so that's a little note. Let's keep it in mind. Now the core part where it actually go and implement the memory. So what we do, always at negative edge of reset or positive edge of clock. We first at reset if it is reset 0. So negative edge clock means it is coming from high to low. Okay, high to low. So ultimately it lands in a value of 0. So if the reset is 0, essentially, then loop through all the address values for I equal to 1. It's not similar to the C or Java statement. Loop through all the address and set all the address to all 0. So again, we use a replicator operator here to save our typing. Now the next part we do, this is not actually done in the real hardware, but it's for our simulation purpose. We want to load the initial program into the memory, right? So there is a read mem h, which means okay, read memory in a hex format. Memory int file, that is a parameter. Remember that parameter we set by default value is memory content .dat, which can be changed at the instantiation time. That file is read into that SRAM storage. See, this is the storage we define here. We do dimensional storage. So what do we see? We'll review the format of the file, but essentially data, certain data is loaded into the memory. Okay, so at the reset time it will read that file, whatever is defined through this parameter, and load into that content into the memory. Now if it is not reset, then if it is read, assign data return register with that content at that address of that SRAM storage, right? And remember, if it is a read, then my data line is going to be driven by that return register, right? So we take care of the read. And if it is a write, read 0, write 1, then we store whatever is coming through the data port into that address. Okay, we are writing back into the storage, and this time this data port is being driven by whoever is driving. Like for our case, it is a processor is writing that data, is driving that data port with some data, and that data is being stored inside the memory. So this is how practically we do model the register, model the memory. Now register filing is nothing but 32 by 32 memory, right? 32 by 32 memory. The address space is like 5-bit address space. The difference is that in that case, if you recall, we'll discuss it later more, but quickly, very quick introduction, that register file, it doesn't have an output, that means it's simpler. It has two output port for 2 register, 2 address port for reading 2 register, and it has a separate data in and I think the write address also. We'll come to that, don't worry, but it's pretty similar to that. You need to define as 2-dimensional storage like this and see if it is a read operation, read some value from that array. If it is write operation, write back some data into the array, and so on and so forth. Now going to the format of that initialization file, it's pretty simple. So at the rate something, this means okay, start loading data from this address. Okay, and then what to be loaded there? These are the all hex values. So it will be loaded at this address. Then next one would be next address, next one would be next address, and so on and so forth. And then of course you can also add some more section, like okay, this section of the memory starting from this address, load this content, all the content. These are all the hex numbers, 32-bit. They all be loaded during the reset time into the memory. Okay, so remember, like if you there are 2 files in the zip project zip file, to dat file, .dat file. Just review that file. It is basically starting from the power up address of the processor with the machine code correspond to the corresponding assembly language program. So it's pretty interesting. So when we when we reset the memory, it will go and load that program into from the power up address, and then in successive clock cycle it will start fetching those instructions and start executing them in the simulation. So this is pretty much it. Now we'll do a little bit of the demo of the memory model. We'll load it in the simulator, Verilog simulator model sim. We'll run the test bench around that. We'll explain what the test bench is doing, and we'll see the memory in action. Okay, so to perform this memory modeling lab for lab 5, what you need to do, you download the prj_2.zip file from the project to assignment, and basically extract all the files. You'll get a lot of v files, and you'll get some dat file, which basically couple of them, this Fibonacci.dat and refib.dat, they are actually the program we'll be using to test our CPU or the processor. It actually has this little program from the power up address of which generate the Fibonacci number. These are the machine code which will be loaded into the memory. Okay, so what we need to do now is to create a project, model sim project, which I have already created one of them, and then why there are two. Yes, I want to quit. Okay, to quit. Okay, so we start the model sim where I have already created the project, and we include all the files. But right now for this lab we are interested in this memory.v file, which we already described. We already know that file, the content of the file, and what they are doing, how it is modeled. All we are interested in the test bench of the memory. So test bench is like this. So from the test bench we need to drive the memory. So that means we need to drive the read, write and reset on the clock, where we define the clock as where, because see here we are actually instantiate some module called clock generator, which will drive the clock signal. We'll review this clock generator later when we start reviewing the project 2 files. But just take it for granted right now that this guy will be creating the clock pulses and sending it into the clock where. Okay, so we defined a bus, data bus with 32-bit index, and this is important. This one is basically saying that this test bench will drive the data bus in the right configuration. Read equals to 0, write equal to 1, which is write the memory. Then you are driving whatever data you need to write in the memory through the data bus. Otherwise it will make it an electrical isolation. It is just opposite to the whatever we had in the memory, inside the memory. Memory needs to drive the data bus when it is a read operation, and whoever is connected to the memory, it needs to drive the data bus during the write operation. Okay, so that's the little bit difference. Now we instantiate the memory, connect all the ports to the registers and the wheres. The only interesting part is that we are now defining, we may not do that at all if we want to just take the default parameter value here, which is the case here, but just for example I put that how we do that. We instance name dot the parameter name, then equals instance name dot parameter name equals a new value. So at the compile time, what Verilog will do, will replace the value of this parameter with the new value defined for that instance. Okay, so we can do multiple instantiation of the same model, same memory, but with different initial file. That's the one functionality. Okay, So now we'll look at that what rest in the test bench. Okay. Why it is not responding? Hopefully it didn't hang. Let me try. Oh. Okay, so I think we passed that problem of hanging anyway. So let's get back. So basically what rest of the code after the instantiation is basically how we are driving the memory. So initializing, beginning the reset with 1, which is non-reset state, read 0, write 0, which is no operation, and then we are assigning data register as all 0, which is to be written, and number of tests, number of pass, and load data is some certain data we are just loading. Okay. Now start the operation at the 10 nanosecond. After 10 nanosecond, we load the reset. So it is a reset operation. So it will wipe out the memory, load the content from the memory content.dat01.dat file. Then we are after again 10 nanosecond we are just resetting, like putting the reset signal to high, so it's a normal mode. Now with the 10 in a loop of 10, what we are doing is basically driving some data in a write mode. So from 1 to address 9 we are writing at that address the same value, like address 1 will be written with 1, address 2 will be written with 2, so on and so forth. Then we are trying to read it back. So we put it in a read. First of all, we just take in a no operation mode. Then this is just a bookkeeping, number of tests plus 1. Then we test if it is a not read or not write mode. Then my data should come out as a IZ. Okay, so that is the first test. Next, we are looking at that from 0 to 10 or 0 to 9 basically. We are trying to set that as a read mode with an address I, and testing the data. If it is not equal to I, that is fail. So what we did at this address from 1 to 9, at each address contains its address value, right? So address 1 will be 1, address 2 will be 2, so on and so forth. So we are reading it back and comparing it with the obtained data from the memory. So if it is something different, then we know the memory is not working. If it is not, then we know there is a pass. Now for the other data, like what we actually preloaded in the memory content.dat file, if you again, let's look at that. What is that? That is basically we are starting this address with this increasing number, right? This is 20, 21, 22 and so forth. So we remember that first data we want to compare is this data. This is the first data of that memory location. So we from the start address that is 0 1 0 0 1 0 0, and then we did like 10 location of that. We are reading back the data, and which has to be the load data starting from 20 blah 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 20, right? And then it will increase for the next address, it will be one more, next address one more, and so on and so forth. So we are just testing that chunk of memory and comparing if it is loaded or not. And if it is everything loaded correctly, it will be all pass and it will get a report. And there is another function called write memh, which will be writing the memory content into this file, memory dump.dat and memory2.dat. From that storage, like memory instance, remember in the memory module we have some storage defined at SRAM 3264M. So this will be access this storage and write all the content from address 00 to F, and here from the dump 2 it will write in hex format, of course, from 00100 till 000100F. okay, from that. So we are accessing that register, array of registers from the memory instance, and writing a part of the memory into the file just for our inspection, what was the content of that memory. Now this is the test bench, so let's run it. Let's go and you'll see there is a compiled mem64tb. We'll load that, okay, and then what we do is basically to load. Let's load some of the signals. Okay, so here memory instance, okay, let's see, this is the wave. Oh, is it? No, not that. I want to load all the driving signal. Let's see. Object, yes. So I'll load this address data, read, reset, write. Okay, we'll observe them. So I to wave, okay, and let's open the transcript window and run all of them. So it takes some time to initialize the 64 memory, and at the end of the simulation we have a $stop here. It will stop, and let's look at the transcript. So yeah, so total number of tests 27. Whatever read write we did, it was all successful. All the tests were done. The waveform looks like this one. Okay, so let's look at, let's bump up a little bit. See, this is the day, this is the clock. I'll just put it on top. This is my reset. I'll do that. Address data, read and write, I will put it on top of that. Okay, so we have the clock signal. We make the reset signal for 1 cycle, and then we have the read signal up during this time, and initially we are all writing, right? So address we are driving 1, 2, 3, 4, etc., and data we are driving from 0 to, from not 0 actually, it is yeah, the same 32 bit. So 1, 2, 3, 4, and see, like when it is a non-read or non-write operation, then the data port is actually IZ. So basically this is the one is working fine, that is a spec. And also during this time, this is a non-read non-write operation, it is IZ. Excuse me. And during the read operation, we are getting back the data out of the memory. Okay, and also at the end of the simulation, what we can see, we have to dump memory dump 1, which is from for the address that first memory dump, write memh, content C, the content 1, 0 to 9 and all 00. after that. And dump 2, which is basically the same file, same dump, same content, right? We did dump from this address. It should contain all the values till that, right? So see, the memory content was loaded correctly and being dumped back from that specific address. So this proves that the memory is working fine and you can use it directly for our project 2 purpose. Okay. So you need to model your register file similarly. We'll talk details about that later, but what you need to understand how this memory model was done, especially significance of this guy, right? This assignment of data port inside the memory and assignment of the data line on the test bench. Assignment of data line on the test bench. If you go and see, yeah, so here, right, they're just an opposite. So this guy needs to drive the data port during the write operation, but inside the memory needs to drive the data port during the read operation. And of course we need to understand what is the parameter, parameterized instance, and so on and so forth. All right, so this is all for the simulation and lab section 5. Please go through this and carefully to perform this experiment yourself and get a feel of this operation of the memory.